The aircraft is already descending. There is no sense of urgency in the cockpit. No alarms.
Descending
No
through flight
raised
level
voices.
240.
Only the
Altimeter
quiet
set.
continuity of routine. An approach that appears stable, predictable, and under control. Outside, the night has absorbed the horizon. There is no visible separation between sky and terrain. The landscape below exists only as an absence of light, a void without detail or depth. In these conditions, altitude is not something that can be seen. It is something that must be believed. Inside the cockpit, the belief is firm. The autopilot maintains a steady descent. The vertical speed is deliberate, controlled. Instrument indications confirm what the crew expects to see. The aircraft is aligned, configured, and moving toward what both pilots understand to be the correct approach path. There is no indication, at least not yet, that anything is wrong. A navigation display glows softly in front of them. Waypoints are plotted. A course line extends forward into darkness, clean and unbroken. The aircraft symbol sits precisely where it should. The system suggests certainty. It always does. One of the pilots adjusts a control input, small, precise. A heading or altitude refinement, the kind of correction made dozens of times in any routine descent. It does not draw attention. It does not need to. Behind that adjustment, something subtle has already shifted. Not in the aircraft's physical behavior, not in the sound of the engines or the feel of the descent. The aircraft continues exactly as commanded, but the assumption underlying that command, the belief about where the aircraft is, has begun to diverge from reality. The terrain below is no longer distant. It rises gradually, almost imperceptibly. There are no lights to reveal it, no visual references to define its slope. The aircraft is descending toward ground that exists in silence, unmarked and unseen. In the cockpit, altitude callouts continue. Numbers are spoken. Confirmations are made. Each callout aligns with expectation. Each response reinforces the same conclusion. The aircraft is where it is supposed to be. There is no contradiction. A radio transmission breaks the silence briefly. Air traffic control provides a routine instruction, clear, concise, unremarkable. The crew acknowledges. Their voices remain steady. There is no hesitation. From the perspective of air traffic control, the aircraft is just another arrival in sequence. From the perspective of the crew, the approach is progressing normally. From the perspective of the aircraft's actual position, neither is correct. The descent continues. Inside the cockpit, attention is divided but structured. One pilot monitors instruments. The other manages communication and cross-checks. This is standard procedure. Roles are defined. Responsibilities are clear. But effective cross-checking depends on a shared understanding of reality. And in this moment, that shared understanding is flawed. A waypoint, entered earlier, accepted without conflict, has placed the aircraft on a path that appears valid within the system. The navigation display reflects this path without warning. There is no immediate indication that the selected point does not correspond to the intended one. The system does not question the input. It executes it. Below, the terrain continues to rise. The aircraft descends through another altitude threshold. The rate remains constant. The engines respond smoothly, maintaining the required profile. Nothing about the aircraft performance suggests danger. The danger is not in how the aircraft is flying. It is in where it is flying. Another call-out. Another confirmation. The cockpit remains composed. Seconds pass in quiet continuity. The kind of silence that often defines the most critical phases of flight. Not empty, but focused. Every instrument is being watched. Every parameter is within limits. And yet, one fundamental truth remains unverified. Position. The navigation display still shows alignment. The course still appears correct. The aircraft symbol continues forward, centered, stable. There is no visual contradiction from outside. There is no immediate contradiction from inside. Only a growing mismatch between the aircraft's true location and the crew's understanding of it. At a lower altitude now, the margin for error has narrowed. Terrain proximity is no longer theoretical. It is immediate, a warning system, designed to detect precisely the scenario, remains silent for the moment, either not yet triggered or not yet recognized as necessary. These systems rely on thresholds, calculations, and timing. They do not anticipate intent. They respond to proximity. The aircraft continues its descent into a space where proximity is rapidly closing. Inside the cockpit, a small detail begins to emerge, subtle, easy to overlook. An altitude that feels lower than expected for this phase. A distance that does not perfectly align with timing. A moment of uncertainty. It is not yet concern, but it is the first deviation from confidence. One of the pilots scans the instruments again, more deliberately this time. The data still appears consistent. There is no obvious fault, no system failure, no warning light demanding attention. Everything is working. Everything is correct, according to the system. The problem is that the system is following an instruction that was never meant to be given. The ground is closer now, still invisible, still silent. The aircraft descends further, and in the final moments before recognition fully forms, before the chain of assumptions is questioned, before the realization becomes undeniable, the situation remains what it has been since the descent began. Controlled, orderly, unaware. The route itself was not unusual. It was a regularly scheduled flight, one of many connecting regional and international networks across terrain that, while challenging, had long been considered manageable within modern aviation standards. The departure airport operated without constraint. The en route phase presented no significant weather systems. Air traffic flow was orderly, predictable. On paper, there was nothing about the flight that suggested elevated risk. The complexity lay at the destination. The airport sat within a region defined not by open plains or coastal visibility, but by terrain that rose unevenly and without symmetry. Hills gave way to mountains. Valleys narrowed into corridors that demanded precision. Unlike airports surrounded by flat expanses, this environment imposed a structure on every arrival. Aircraft could not simply descend in a straight line. They had to be guided. The published approach procedures reflected this reality. They were designed carefully, built around navigation fixes that directed aircraft along safe paths through terrain. Each waypoint served a purpose, positioning the aircraft laterally while controlling descent profiles vertically. But these procedures relied on one critical assumption, that each waypoint was correctly identified. The navigation infrastructure in the region had evolved over time. Traditional ground-based navigation aids, VORs, NDBs, remained in use, supplemented in some aircraft by more advanced systems, such as flight management systems, FMS, and inertial navigation. However, not all systems interpreted information in the same way. Waypoint naming conventions, in particular, introduce a subtle vulnerability. Some navigation databases contain multiple fixes with similar or identical identifiers, differentiated only by context or geographic region. In most cases, this posed no issue. Pilots were trained to verify coordinates, cross-check positions, and ensure the selected waypoint matched the intended route. But the system itself did not inherently prevent selection errors. It assumed correct input. Air traffic control in the area operated within its own limitations. Radar coverage, while present, was not always precise at lower altitudes, especially in regions where terrain interfered with signal clarity. Controllers relied on position reports, procedural separation, and the expectation that aircraft were following assigned routes accurately. This structure worked, so long as the aircraft remained where it was expected to be. The margin for deviation was small. Over the years, there had been indications, subtle, often overlooked, that navigation in the region demanded more than routine attention. Reports of minor track deviations, occasional confusion over waypoint identification. None had resulted in catastrophe, but each pointed to the same underlying condition. The system depended heavily on human verification. At the time, terrain awareness technology was not uniformly implemented across all aircraft. Some were equipped with early versions of Ground Proximity Warning Systems, GPWS, designed to alert crews to imminent terrain conflict. However, these systems were reactive rather than predictive. They responded to closure rates and altitude thresholds, not to navigational intent. They could warn, but they could not prevent. The airline operating the flight adhered to standard industry practices. Its procedures emphasized compliance with published approaches, adherence to air traffic control instructions, and proper use of onboard navigation systems. Training programs addressed instrument flying, system management, and crew coordination. Yet, like many operators of the era, certain assumptions remained embedded in routine. That navigation inputs, once verified, remained correct. That automation, once engaged, would maintain the intended path. That deviations would be obvious. These assumptions were not unreasonable. They were based on consistent experience, but they were not infallible. The approach into this particular airport required careful sequencing of navigation fixes. Each waypoint guided the aircraft through a safe corridor, ensuring adequate terrain clearance while positioning for final approach. The vertical profile was equally important. Descending too early or too late could disrupt the balance between altitude and terrain. Accuracy was not optional. It was essential. In normal operations, crews would brief the approach thoroughly. They would review charts, confirm waypoint identifiers, set navigation radios or program the flight management system, and cross-check entries. This process was designed to catch discrepancies before they could influence the flight path. But the effectiveness of this process depended on time, clarity, and shared understanding. Under certain conditions, high workload, subtle ambiguity, or simple familiarity, verification could become confirmation. Inputs could be accepted because they appeared correct, not because they had been rigorously validated. The environment did not forgive such shifts. Terrain, unlike weather, does not move. It does not change in response to aircraft position. It remains constant, indifferent to human expectation. An aircraft ascending along an incorrect path will not encounter resistance from the system guiding it. The autopilot will continue to follow commands precisely. The navigation display will continue to present a coherent picture, one that reflects the data it has been given. If the data is flawed, the coherence becomes misleading. In the years leading up to the accident, the aviation industry had begun transitioning toward increased reliance on automated navigation. Flight management systems allowed for more efficient routing, reduced pilot workload, and improved fuel management. But they also introduced a new layer of abstraction. Pilots no longer navigated solely by raw data. They navigated by interpreted data. This shift required a different kind of vigilance, not just monitoring aircraft performance, but continuously validating the assumptions embedded within the system. At this airport, in this terrain, that distinction carried significant weight. The final approach segment was particularly sensitive. By the time an aircraft reached this phase, altitude margins were reduced. Terrain clearance depended on strict adherence to the published path. Any deviation, lateral or vertical, could place the aircraft outside the protected corridor. There would be little time to recognize the error, less time to correct it, and no external visual reference to provide warning. The night conditions removed the final layer of redundancy. In daylight, terrain might be visible. Slopes, ridgelines, and horizon cues could provide context, even if navigation data were imperfect. At night, those cues disappeared. The outside world became an indistinct void, offering no information beyond the absence of light. In such conditions, instruments are not just primary, they are absolute. The crew of the aircraft entering this environment carried with them all the tools required to complete the flight safely. The aircraft was capable. The procedures were established. The route was known. What remained uncertain, what would only become clear later, was whether the alignment between intention, input, and reality had already begun to separate. Not dramatically, not in a way that would immediately draw attention, but enough to place the aircraft on a path that, while appearing correct within the system, no longer corresponded to the safe corridor defined by terrain. Understanding the accident requires separation, not of time, but of perspective. The aircraft, the crew, the environment, and the systems each function within its own logic, its own constraints. None failed in isolation. None acted independently of the others. The outcome emerged from their interaction, where assumptions aligned just enough to conceal developing error. The aircraft itself was fully capable of completing the flight. It was equipped with a standard suite of avionics for its class and era, navigation radios, autopilot systems, and a flight management system designed to integrate routing, performance, and positional awareness into a single interface. These systems reduced workload and allowed for precise control, particularly during complex phases such as descent and approach. The autopilot, once engaged, followed commands with consistency. It did not question intent. It interpreted inputs, headings, altitudes, vertical speeds, and executed them exactly. In this way, it represented one of the most reliable components in the entire chain. Reliability, however, is not the same as awareness. The aircraft did not possess an inherent understanding of terrain beyond what its systems were designed to detect. If equipped, the ground proximity warning system provided alerts based on altitude and closure rate, but it did not evaluate the correctness of a navigation path. It did not compare intended routing with actual terrain clearance in a predictive sense. It reacted to proximity, not to error. The flight management system introduced a layer of abstraction. Instead of navigating directly via raw radio signals or visual checkpoints, the crew interacted with a representation, a digital route composed of waypoints, each defined by coordinates stored in a database. When a waypoint was selected, the aircraft did not know why it had been chosen. It simply navigated toward it. This design assumed that the selection process itself was accurate. The system provided tools, coordinates, identifiers, sequencing, but the responsibility for correct input remained with the crew. In most operations, this structure functioned without issue. In this case, it created a condition where a single incorrect input could propagate through the system without immediate contradiction. The aircraft would continue to behave normally, even as it followed an unintended path. Crew. The flight crew operated within established procedures. Both pilots were trained, qualified, and experienced within the operational framework of their airline. They were familiar with instrument flight, with automated systems, and with the general demands of approach into terrain-sensitive environments. Their actions in the cockpit reflected routine discipline. Tasks were divided. One pilot maintained primary control and monitored flight parameters. The other managed communications, navigation inputs, and cross-checking duties. This structure, central to crew resource management, was designed to reduce individual workload and increase overall situational awareness. But CRM is only as effective as the information it is built upon. If both pilots share the same incorrect assumption, cross-checking becomes confirmation. The approach phase inherently increases workload. Descent planning, altitude restrictions, communication with air traffic control, configuration changes, each requires attention. Time compresses. Decisions must be made efficiently. Under these conditions, verification processes can become streamlined. A waypoint entered and appearing correct on the display may be accepted without deeper validation. The name matches expectation. The system accepts it. The route appears coherent. There is no immediate reason to challenge it. Fatigue, while not necessarily pronounced, may also play a subtle role, not in the sense of impairment, but in reduced cognitive flexibility, the ability to question assumptions or detect inconsistencies that fall just outside routine expectation. The crew did not act irrationally. They acted consistently with what the system presented to them. Their understanding of position, altitude, and trajectory remained internally coherent. It was the foundation of that understanding that had shifted. Environment. The environment imposed its own structure. Terrain in the region did not rise sharply in a single, obvious formation. It built gradually, in layers that were difficult to perceive without visual reference. Valleys narrowed without clear boundaries. Elevation increased without dramatic visual cues. At night, this complexity became indistinguishable. There were no horizon lines to define altitude, no scattered lights to outline terrain contours. The absence of visual information created a uniform darkness in which distance, scale, and elevation could not be judged externally. Weather conditions did not necessarily present as severe. There may have been cloud layers, haze, or reduced visibility, but nothing that would independently justify concern. The environment did not actively interfere with the aircraft. It simply removed external reference. This placed full reliance on instruments. In such conditions, even a perfectly functioning aircraft can become vulnerable if the information guiding it is incorrect. Without visual cues, there is no secondary system, no instinctive correction based on sight. The terrain remains where it is. The aircraft continues where it is directed. The intersection of those two paths becomes inevitable if not identified in time. Systems. The navigation system represented the central point of interaction between human intent and aircraft behavior. At its core was a flight management system database, a collection of waypoints, routes, and coordinates. Each waypoint was identified by a name, often composed of letters that held meaning within a regional or procedural context. However, these identifiers were not always unique globally. Similar or identical names could exist in different locations. In some cases, multiple entries could appear within the system, differentiated only by subtle data fields, latitude, longitude, or associated route structures. Selection required attention. The interface presented options, but it did not enforce correctness. It did not verify that the selected waypoint matched the intended procedure beyond basic logical sequencing. Once selected, the system integrated the waypoint into the active route. From that moment forward, all guidance, lateral navigation, distance calculations, estimated times, was based on that selection. The autopilot followed this guidance precisely. Mode awareness became critical. The aircraft could operate in various navigation modes: heading select, lateral navigation, LNAV, vertical navigation, VNAV, or combinations thereof. Each mode determined how the aircraft interpreted inputs and adjusted its flight path. A crew confident in LNAV engagement, for example, would expect the aircraft to follow the programmed route automatically. If that route contained an error, the automation would not reveal it. It would reinforce it. Warning systems, if present, existed outside this navigation logic. Ground proximity warning systems monitored altitude and terrain closure rates. They were designed as a last line of defense, but they operated within thresholds. If the aircraft descended in a controlled manner, aligned with what appeared to be a normal approach profile, warnings might be delayed until the margin for recovery had already narrowed significantly. In some cases, alerts could be misinterpreted. seen as nuisance warnings or triggered by known terrain features during otherwise safe approaches. This created a potential hesitation, a moment where the system's warning competed with the crew's expectation. And expectation, when reinforced repeatedly by consistent instrument indications, often carries more weight. Convergence. Individually, none of these elements represented failure. The aircraft functioned as designed. The crew operated within procedure. The environment remained stable. The systems executed commands accurately, but the interaction created a closed loop. An incorrect navigation input, small, almost unremarkable, entered the system. The system accepted it. The aircraft followed it. The crew monitored it. Each element confirmed the others. There was no immediate contradiction, only a gradual divergence between perceived position and actual position. By the time that divergence became detectable through external means, terrain proximity, altitude discrepancy, the available time to respond had already diminished. What remained was not a sudden breakdown, but the continuation of a process that had been consistent from the moment the incorrect input was accepted. The descent continues. By now, the aircraft has left the relative safety of higher altitude. The margin between control flight and terrain has narrowed to a space measured not in thousands of feet, but in moments. Inside the cockpit, the sequence remains structured. Altitude restrictions are being met. Headings are stable. The navigation display continues to show alignment with the program route. From a procedural standpoint, the approach appears disciplined, but the aircraft is no longer where the crew believes it to be. The divergence, small at first, has become operationally significant. The waypoint entered earlier has guided the aircraft of the intended approach corridor, not dramatically, not in a way that would trigger immediate suspicion. The path still appears logical within the system. The geometry of the route remains clean, but it no longer corresponds to the terrain clearance built into the published procedure. The aircraft is descending along a path that has no protection. A radio transmission is received. Air traffic control issues a descent clearance. Routine, expected. The crew acknowledges. Their understanding of position aligns with the instruction. There is no reason to question it. From a controller's perspective, the aircraft is following a known arrival path. From the crew's perspective, they are complying correctly. The system, however, is guiding them elsewhere. The autopilot maintains the descent. Vertical speed remains steady. There is no abrupt movement, no instability. The aircraft behaves exactly as commanded. Inside the cockpit, attention shifts briefly between tasks, monitoring altitude, confirming navigation, preparing for the next phase of approach. Each action is deliberate, measured. Time continues to compress. The aircraft passes through another altitude gate. The number is called. It matches expectation. The descent profile appears intact, but outside, the terrain has risen to meet that altitude. Still invisible, still unacknowledged. A subtle discrepancy begins to form. Distance to the next waypoint feels inconsistent with expected timing. The aircraft appears closer, or perhaps further, than it should be at this stage. It is not an obvious error. It does not trigger immediate concern, but it introduces uncertainty. One of the pilots reviews the navigation display again. The route line remains centered. The waypoint sequence appears correct. There is no break in continuity, no alert, no indication that the system's internal logic has diverged from reality. The system confirms itself, and in doing so, reinforces the assumption that it is correct. The aircraft descends further. Altitude now approaches a level where terrain clearance becomes critical. In a correctly flown approach, this phase would place the aircraft within a protected corridor with sufficient distance from surrounding elevations. Here, that protection does not exist. The terrain rises into the aircraft's path. Inside the cockpit, another small cue appears, subtle, but different. An altitude that seems low relative to the perceived phase of flight. A momentary pause. It is not yet recognition, but it is no longer complete certainty. One pilot scans outside. There is nothing to see. No lights. No horizon. No terrain. The absence of visual reference removes the final opportunity for intuitive correction. The aircraft continues descending. Now, the closure rate with terrain is increasing. Not dramatically, but steadily. The vertical profile, while smooth, is no longer appropriate for the environment below. A system designed to detect this condition begins to process the data. Altitude, descent rate, terrain proximity. It calculates, and then a warning. It is abrupt, distinct, and out of context with the calm that has defined the approach. A terrain alert. For a fraction of a second, it exists without interpretation. Then it is processed. The crew reacts, not with panic, but with rapid reassessment. The warning contradicts their understanding of position. It suggests that the aircraft is closer to terrain than expected. But expectation is deeply established. The navigation display still shows alignment. The descent profile appears correct. The warning competes with a system that has, until now, provided no reason for doubt. A decision point emerges. Seconds pass. The aircraft continues descending. The terrain is now critically close. Another warning, more urgent. The tone changes. This is no longer advisory. It is immediate. Recognition begins to form. The possibility that the aircraft is not where it should be becomes real. But recognition requires confirmation. And confirmation requires time. Time that is no longer available. The crew initiates a response. Power is increased. The autopilot may be disengaged or overridden. A climb is commanded. The aircraft begins to react. But inertia, both physical and procedural, introduces delay. Engine spool. Pitch increases. The descent arrests. But the terrain has already closed the gap. In the final seconds, the sequence becomes irreversible, not because the aircraft cannot climb, but because the recognition of error has come too late to allow the climb to be effective. The aircraft, still under control, still responding to inputs, intersects with terrain that was never part of the intended path. There is no deviation in structure, no loss of control in the traditional sense, only a continuation of flight into an environment that the crew did not know they had entered. In the immediate aftermath, there is no clarity, only location. The aircraft has come to rest in terrain that is difficult to access, far from major infrastructure, and largely obscured by the same environmental conditions that contributed to the accident itself. Night gives way slowly to first light, revealing the geography in detail for the first time, not as an abstract absence, but as a defined landscape of rising ground, uneven slopes, and confined space. The scale of the environment becomes evident. So does the precision required to navigate it safely. Emergency response begins with uncertainty. Coordinates are approximate. Initial reports rely on last known position, fragmented communication, and radar data that offers only partial resolution at lower altitudes. Search and rescue teams move toward the area, but terrain dictates pace. Access routes are limited. Helicopters operate within visibility constraints. The process is methodical. There is no immediate explanation for what occurred. The aircraft had not reported distress. There were no indications of mechanical failure transmitted to air traffic control. The descent had appeared routine. This absence of warning shapes the early stages of investigation. Attention turns first to the aircraft itself. Recovery teams locate the flight data recorder, FDR, and cockpit voice recorder, CVR. These devices, designed to withstand impact and preserve the final moments of flight, become the primary source of objective information. They are transported to analysis facilities where data extraction begins. The reconstruction is precise. Every parameter is reviewed: altitude, airspeed, vertical speed, heading, navigation inputs. Each recorded value contributes to a timeline that must be understood without assumption. The initial findings confirm what had been observed externally. The aircraft was under control. There was no evidence of structural failure. Engines were operating. Flight control systems responded to inputs. The descent profile, while ultimately unsafe, was stable and consistent. This eliminates one category of cause. The focus shifts. Cockpit voice recordings provide context to the data. Conversations are reviewed, not for emotion, but for information. The tone remained composed throughout most of the descent. There are no indications of confusion or alarm until the final moments. This detail becomes significant. It suggests that the crew's understanding of the situation remained intact until very late in the sequence. The investigators begin to examine navigation. The flight management system data reveals the route as programmed during the approach phase. Waypoints are listed. Sequencing is analyzed. Coordinates are compared against a published procedure for the intended arrival. It is here that the divergence becomes visible. A waypoint, selected earlier in the descent, does not correspond to the intended fix in the approach chart. The identifier matches in name, but the coordinates differ. The system has accepted the selection without conflict, integrating it into the active route. From that point forward, the aircraft's navigation guidance was based on an incorrect reference. The deviation is subtle in appearance. On the navigation display, the route remained continuous. There are no abrupt turns or discontinuities that would immediately signal error. The geometry is smooth. The aircraft follows the programmed path exactly, but that path leads away from a protected corridor. Investigators reconstruct the lateral deviation. Using recorded position data, they map the aircraft's actual track against the intended approach path. The difference is not extreme, but it is enough. Enough to remove terrain clearance. Vertical analysis confirms the second component of the chain. The descent profile, while consistent with the crew's expectations, did not align with the actual terrain elevation beneath the aircraft's path. At specific points where safe altitude margins should have existed, the aircraft was already below the minimum required for that location. This condition developed gradually. There was no single moment where safety margins disappeared. They eroded. Investigators then examined system behavior. The ground proximity warning system is reviewed in detail. Data indicates that alerts were generated. Timing is critical. The first warning occurred when terrain closure reached a threshold consistent with GPWS logic. Subsequent warnings escalated in urgency. However, the interval between initial alert and impact was limited. The system functioned as designed. It warned, but it did so within parameters that did not allow sufficient time for recovery once the aircraft had entered the unsafe profile. Attention returns to the cockpit. Why was the incorrect waypoint not detected? Why did cross-checking procedures fail to identify the discrepancy? The investigation identifies several contributing factors. First, the similarity of waypoint identifiers. The system presented multiple entries with comparable naming conventions. Without cross-verifying coordinates or contextual data, selection error remained possible. Second, the interface design. The flight management system did not provide prominent differentiation between similarly named waypoints beyond textual information. There was no visual or procedural barrier preventing incorrect selection. Third, confirmation bias. Once the waypoint was entered and the route appeared coherent, subsequent checks validated the display rather than the underlying data. The system's consistency reinforced the belief that it was correct. Fourth, workload. During descent and approach, task saturation increases. Navigation inputs, communication, and aircraft configuration occur in parallel. Under these conditions, verification steps can become abbreviated. None of these factors alone would necessarily lead to an accident. Together, they form the chain. The investigation concludes that the primary cause of the accident was a navigation error resulting from incorrect waypoint selection, leading to controlled flight into terrain. Contributing factors include inadequate cross-verification of navigation inputs, ambiguity in waypoint identification within the navigation database, lack of predictive terrain awareness systems, environmental conditions limiting visual cues, high workload during approach phase. The findings extend beyond the flight itself. They highlight systemic vulnerabilities. Regulatory authorities review the implications. The accident is not isolated in its mechanisms. It represents a broader challenge within modern aviation. The interaction between human operators and increasingly complex automated systems. Industry response begins with analysis, then moves toward action. Manufacturers examine interface design. Opportunities for clearer waypoint differentiation are identified. Database management practices are reviewed. Standardization efforts gain momentum. Airlines reassess training. Emphasis is placed on navigation verification procedures. Specifically, the requirement to cross-check waypoint coordinates, not just identifiers. Crew resource management programs are updated to address confirmation bias and reinforce independent verification between pilots. Regulators consider the role of terrain awareness technology. Enhanced ground proximity warning systems, EGPWS, capable of providing predictive terrain mapping rather than reactive alerts, become a focus. Their ability to display terrain relative to aircraft position introduces a new layer of situational awareness. Implementation takes time, but the direction is. In aviation, accidents do not end with impact. They continue, quietly, methodically, through analysis, revision, and change. The aircraft is gone. The flight cannot be repeated, but the conditions that led to it can be examined, understood, and, over time, reduced. This process is deliberate. It does not seek dramatic conclusions. It seeks precision. The findings of the investigation do not point to a single failure that can be removed to prevent recurrence. Instead, they reveal a system that depended on alignment between human input, machine interpretation, and environmental reality. In this case, that alignment was lost, not abruptly, but gradually, through a sequence of decisions and confirmations that appeared valid at each step. The legacy of the accident begins with this understanding. Navigation systems, once viewed primarily as tools for efficiency and workload reduction, are reassessed through a different lens. Their accuracy is not in question. Their reliability remains intact. What changes is the recognition that accuracy depends on input, and input depends on verification. Aircraft manufacturers begin to refine interface design. Waypoint selection pages are modified to provide clearer contextual information, geographic coordinates, region identifiers, and improved sorting logic. The goal is not to eliminate human interaction, but to support it with better clarity. Ambiguity, where it exists, is reduced. Navigation databases undergo standardization efforts. Naming conventions are reviewed. Duplicate or similar identifiers are managed with increased attention to differentiation. The intention is to minimize the possibility that two distinct locations can be confused through interface presentation alone. These changes are incremental, but they are persistent. At the operational level, airlines revise procedures. Navigation input is no longer treated as a single-step task. It becomes a process requiring explicit cross-verification. Crews are trained to confirm not only the name of a waypoint, but its position, using charts, raw data, or independent system references. The emphasis shifts from confirmation to validation. Crew resource management evolves alongside this shift. Training programs incorporate scenarios that challenge assumptions. Pilots are encouraged to question consistency when it appears too complete, when every system agrees, but external context is limited. This is not a rejection of automation. It is an adjustment to its role. Automation remains essential. It provides precision, reduces workload, and enables operations in environments that would otherwise be inaccessible. But it is no longer treated as self-validating. It requires oversight. The most visible transformation emerges in terrain awareness technology. Enhanced Ground Proximity Warning Systems, EGPWS, introduce a new capability, predictive terrain mapping. Instead of waiting for altitude and closure rates to reach critical thresholds, these systems compare the aircraft projected path with a database of terrain elevations. They display, they anticipate, they provide crews with a visual representation of terrain relative to their position, even in complete darkness. In environments where visual reference is absent, this becomes a critical layer of defense. An aircraft descending along an incorrect path is no longer guided solely by abstract navigation data. The terrain itself becomes visible within the system, an independent reference that can contradict an incorrect route before proximity becomes critical. This does not eliminate error, but it changes the moment at which error becomes visible. Regulatory authorities incorporate these technologies into broader safety frameworks. Requirements evolve. Recommendations become standards. Over time, fleets are equipped, procedures updated, and training aligned with new capabilities. The changes extend beyond equipment. They influence philosophy. The accident reinforces a principle that had always existed, but had become less visible with the rise of automation. That situational awareness is not a product of any single system. It is the result of continuous comparison between what is expected and what is observed, between what the system displays and what independent references suggest, between assumption and verification. The environment where the accident occurred remains unchanged. The terrain has not shifted. The valleys and slopes continue to define the same boundaries. Aircraft still approach the airport under similar conditions: night, weather, limited visibility. But the way those approaches are conducted has evolved. Pilots now operate with additional layers of information. Systems provide earlier warnings. Procedures demand deeper verification. Training emphasizes not only how to operate the aircraft, but how to interpret and challenge the information it provides. The silence that once defined the final moments of that flight is no longer as complete. There are more cues, more opportunities to detect divergence, more time, however limited, to respond. And yet, the fundamental dynamic remains. Aircraft still rely on human input. Systems still execute commands without judgment. Terrain still exists independent of perception. The balance between these elements continues to define the safety of flight. The accident does not represent a failure of aviation as a system. It represents a moment where the system revealed its limits. From that moment, adjustments were made, not to eliminate complexity, but to manage it more effectively. The legacy is not visible in a single procedure or device. It is distributed across checklists, training sessions, software updates, and cockpit habits. It exists in the quiet act of verifying a waypoint coordinate, in the decision to cross-check one more time, in the awareness that a correct-looking display is not, by itself, confirmation of reality. These are small actions, individually unremarkable. Collectively, they define the difference between alignment and divergence, between controlled flight and controlled flight into terrain.